Okay, in this problem, we're looking at an elastic collision. We've got two beads. You can see the beads are placed at different points on a wire here that they both slide. You can see bead A is placed at 1.5 meters above that of the center of B. So we have a 0.4 kilogram green bead that slides on a curved frictionless wire starting from rest at point A. At point B, the bead slides elastically, or collides elastically with a 0.6 of a kilogram blue bead at rest. They want us to find the maximum height that the blue bead moves up the wire when a bead smacks it. So, we're looking at an elastic collision. So, in taking a look at this, based on what we just saw here, we've got really two problems here. You can see the divider here that divides between the two problems. We've got the problem where the A bead slides down the wire until it makes impact with the B bead. At that point, the problem starts over again, and we have the problem where B bead then is moved up the wire a distance due to the head-on collision. Okay, so in both cases we're going to solve for the energy based upon the height of the beads. So let's take a look at problem number 1. We're looking at bead A sliding down the wire and creating some energy as it's coming down, potential to kinetic, and hits B. So what are we given in the problem? Well, the things that we've already covered here. We know that bead B is a 0.4 of a kilogram. I thought this marker was going to work. Bead A is at 1.5 meters above B, and we have the mass then of bead B at 0.6 of a kilogram. So for the first part here, we're going to get rid of that. We're going to solve using the conservation of mechanical energy. So we lay out our relationship that says the kinetic energy of bead A added to the potential energy of bead A initial is equal to the kinetic energy of bead A plus the potential energy of bead A final. Okay, so that's our initial and final energy problems. So to find the speed of the green bead at the point B just before it collides. So we want to find it just instantaneously before A collides with B, and we have another process happening. So if we write our relationships for kinetic energy and potential energy, we see 1/2 mv squared initial, mgh, in this case y A initial, is equal to 1/2 mv squared on the other side, mgh or mgya on the other side. So as we do with all of these problems, we look for the terms that go to 0 because maybe they had an initial velocity of 0, and that is the case with the kinetic energy. So that goes to 0. On the other side of the relationship, when the bead reaches the bottom then of the arc here, just before it hits B, we're going to say that the bead stopped. So at that point, we're going to stop action, and all of the height then goes to 0. So that term goes away. So we're left with the two terms. The height is equal to the velocity. Okay, so we've got that term of potential energy versus kinetic energy. Again, the masses on both sides are the same, so they cancel out. So we're just left with the terms gravity times the height is equal to 1/2 the velocity squared. So let's calculate, in this part of the problem, the velocity of the bead just before it hits bead B. Okay, so we have all of our terms. Let's move terms around, solve for the velocity. When we do that, we end up with the velocity of A final, that's down here at the bottom, is equal to the square root of 2 times g times the velocity initial. So there are all of our terms. We can put them under the radical, solve, and we end up with a velocity A final of 5.42 meters per second. So at this point, we're going to say that the two beads then are going to share that velocity. That becomes the initial velocity of bead B. So now let's look at the point where the two beads do in fact collide. So we've moved forward a microsecond. Okay, so since we have said, solving under the condition of conservation of momentum, that we have the velocity of A equal to the velocity of B, 5.42 meters per second at the point of impact. So now we write our relationship that says the mass and velocity of the first bead plus the mass and velocity of the second bead is equal to the mass and velocity of both before and after. Again, look for the terms that go to zero. Mass and velocity associated with bead B on this side of the relationship. B is at zero, so that simplifies the problem down to just mass 1 velocity A is equal to the reaction that occurs on the other side. So we put our values in, 4/10 of a kilogram, 5.42 meters per second, add our masses in on the other side, and solve then for our relationship. So what we want to really set up here is a relationship that says we have a one in terms of the other. Okay, so now we have all of the terms except for the velocity of A at the point of collision and the velocity of B then at the point of collision. So we knew the initial values, we didn't know the final value. So that's as far as we can go with that part of the problem. So let's switch to another method and see if we can solve for anything else. So at this same point, we're going to look at a head-on elastic collision. So we have the velocity of bead final plus the velocity of bead initial is equal to the velocity of A final plus the velocity of B final. Knowing that as we have taken the values instantaneously, at that point B is not moving, A is moving at this velocity. So we can put those values into that relationship, and we see that term again goes to zero, the velocity of B initial and the velocity of A initial. So now we have a term for V velocity of B final is equal to velocity A plus the initial velocity. Okay, so with that value, since we know that one is equal to the other here, we can substitute 5.42 here. Okay, actually we're just moving terms around. 5.42 is equal to VA plus 1.5 times VB. Okay, so we're using the other expression that we've already solved for. Okay, and now we're going to substitute this term in for VB. Okay, so as we move along here, we're looking for places where we can do substitutions and solve one in terms of the other. So as we move our terms around, then velocity A final is equal to all of this term that we just substituted is equal to 5.42. So let's see how many of the terms we can combine and move things around. Well, this is just a number, this is a number, this is a number, and this is a number. So the only thing we have left is what is velocity of A doing right at the point of the head-on collision. So let's gather all of our terms together, all of our number terms together, move everything to the other side of the equation such that we have the velocity A final by itself. And solving this through, we end up with a minus 1.08 meters per second of velocity A final. So we can take that value now, put it into the relationship we solved for at the top of the page, and we end up with then a term that says the velocity of bead B final at the point of impact, that's all we're talking about, is this one snapshot in time, is 4.34 meters per second. Okay, so now we've moved through two parts of the problem. Now let's see what happens then once bead B is hit and it starts sliding up the wire. So we're looking for the maximum height that the bead B, the blue one, moves up the wire. So we go back to our conservation of mechanical energy relationship, use our energy terms, convert them all to our known mass, velocity, height, gravity terms. Again, look for the terms that go to 0. At this point, every term that had B initial goes to 0. Every term that had B final should have a 0 value once it reaches the top. So we're left with then 1/2 mv squared is equal to mgh, or mgy. Masses cancel out again. Now we're left with a simplified term. Let's move everything around so that we can solve for what y, the height of blue bead, is at the end of the process here. So moving the gravity and leaving the 2 times where it is, we end up with the y height of B final then is equal to 4.34 meters per second squared divided by 2 times the acceleration of gravity. And now we can see that the bead travels up almost 1 meter, 0.960 up the wire. So with this problem, you can see that it involved looking at several steps and breaking the problem down into several really boundary value problems. You determine where the boundaries are and solve between those boundaries. The end of one problem becomes the beginning of the next problem. So you can use the initial and finals then for each of those. I hope that helped. Thank you.